Yellowstone isn't sitting on a lake of lava at all. It's sitting on something much weirder and honestly much harder to predict. The headline picture, the one in every textbook, turned out to be wrong. This is a lot closer to your feet than anyone ever drew it. Not slightly wrong. Actually, to discover how thin our confidence was to begin with, they kind of knew that something's off with their description. The behavior of the next act depends on the source, and we just found out that we got the source wrong. So every model of a future eruption has to be rebuilt. Problem is, it did not light up. It's a ghost. That blob, that chimney, it wasn't there. There's news from Yellowstone, and this changes everything because a volatile ridge cap is sitting just above Yellowstone's magma reservoir, and that is actually reshaping how scientists understand what keeps the supervolcano running. And that is game-changing because this volatile cap, it changes the Yellowstone risk calculus. So the practical stakes are really straightforward, and we will look at them in this video because Yellowstone hosts millions of visitors each year, and the park sits on top of a system that has produced 3 caldera-forming eruptions over the past 2.1 million years. And we've had some weird things going on in the recent 2 years with these phreatic eruptions and with the new pools that have formed. I've reported about this, so let's look into this, guys. For 50 years, every textbook, every documentary that you might have seen, every diagram you have ever seen of Yellowstone had one thing at the center of it. Basically a giant column of molten rock, magma, that is basically rising straight up from deep inside the earth, like a chimney, a blowtorch that is pointed at the bottom of North America, like this blob that is underneath. So forget about this now. There's a team that just a few weeks ago of scientists that has built the most detailed 3D model of what's underneath the Western United States. That model is the most detailed anyone has ever made. And the stunning results were that blob, that chimney, it wasn't there. It wasn't there. But what they found instead was even stranger. The heat under Yellowstone isn't coming up. You might now say, oh, that's a good thing. No. It's coming sideways. And this is a lot closer to your feet than anyone ever drew it in any of these maps and graphics and pictures and animations. So there's 3 things that I need to show you right now, and I'm going to show them in order because they only make sense when we stack them like this. So listen to this, guys. Number 1, why the old theory quietly stopped working and the piece of evidence that broke it. That's what we will look into. Number 2, the thing they're calling a mantle wind and what that means and why it means that Yellowstone isn't sitting on a lake of lava at all. It's sitting on something much weirder and honestly much harder to predict, which isn't good when we're talking about a supervolcano. And number 3, and stay for this one, guys, when I come to this one, because this is the part that actually made me sit back and say, what is it that this new model says about where Yellowstone is actually going? Because it's moving. It has been moving for 17 million years, and there's something in its path. But let's start at the beginning until we get there. So, quick, dumb, simple question, because half of what people think about Yellowstone is wrong from the first sentence. I have to say that. Yellowstone is not a mountain. We know that. That's the first thing. But When you picture a volcano, you picture a cone with a hole on the top. Yellowstone has no cone. Yellowstone is a hole, a crater that is roughly 30 by 34 by 45 miles across. So big that when you're standing in it, basically in the Yellowstone Park, taking pictures of the elk and all the bubbling pools, you can see that. You don't feel it, you don't notice that. You're inside of it, and the rim is basically over the horizon. So that crater, we call that a caldera. And a caldera is what you get when the ground doesn't basically explode outwards. It collapses downward because everything underneath just left. Well, what left? It has done that twice in the last 2.1 million years. Once about 2.08 million years ago, and again 630,000 years ago. Each one threw out somewhere between 1,000 and 2,500 cubic kilometers of rock and ash, volcanic eruption, magma. So here's the scale if we look at human terms, right? Mount St. Helens in 1980, the scary one that everyone remembers, the one that flattened forests and made the national news for over a month, was about 1 cubic kilometer. I just said Yellowstone, 1,000 to 2,500 cubic kilometers. So one, Yellowstone's last one was in the ballpark of 1,000. Anything over 1,000 basically gets its own category. So scientists call this a super eruption, and there are only about 20 places on Earth that are even capable of one, right? The reason we care isn't the crater itself, it's the ash and the sulfur in the sky afterwards. That's enough to dim the sunlight and to drop global temperatures for years. And we all know what that causes, right? You can't grow, you can't, so many things. Famine is happening and huge problem. So this is a system that is worth understanding, and which brings us to the, well, I have to say, embarrassing part. So let's talk about the old theory and the crack in it. So we didn't understand it, right? The standard explanation was the mantle plume. So picture a lava lamp. You heat the bottom of the lava lamp, then a blob of hot wax detaches and it rises in a column straight up, basically. So the idea was that basically the Earth does the same thing. A plume of superheated rock is rising from way deep down near the core, and then it's burning a hole through the plate above it, basically like holding a blowtorch towards the surface. And then it's like that is held under a sheet of metal, like, and then the volcano has a caprock layer. So, and that theory had one enormous point in its favor, which is that Yellowstone is in the wrong place. Almost every volcano that you can name sits on the edge of a tectonic plate. Pacific Ring of Fire, subduction zones, we have the volcanoes there. Plate boundaries, that's usually the rule. Yellowstone is nowhere near an edge. It's parked in the middle of a continent 1,000 miles from anything, and it's doing this. So a blowtorch from below was the obvious way to explain the thing, right? To explain basically a hot spot in the middle of nowhere. But the problem is what the blowtorch predicts. So hear me out. A blowtorch gives you a narrow, focused hotspot, right? 1 point. What we actually measure at Yellowstone is a heat system that is broad, lopsided, and tilted. It leans off to the southwest in a long shape, like more like a smeared streak than a dot. But there's a second problem, and that is seismic imaging. That is basically a CT scan of the Earth, and you're using earthquake waves to do that. And that kept coming back ambiguous. So if there is a clean column running from near the core up to Yellowstone, it should light up in these scans. Problem is, it did not light up. It did not light up the way a textbook plume should. So you have a theory that explains why there's a volcano, but not what it looks like. And for years, that was just an uncomfortable footnote of somewhat that nobody had the computing power to resolve. They all knew there is a flaw in how they describe it until this new study. So this new model, the mantle wind, sounds interesting. So the team built a high-resolution, three-dimensional simulation of the entire western half of North America. So basically the rigid outer shell of the planet and the slow-flowing layer that's underneath it. And then this model, they used it and they let it run like to real present-day physics. And the heat didn't come up from the deep. It came in from the side. So two layers, and you need both. So the lithosphere is basically the outer shell. It's the crust plus the very top of the mantle. It's rigid, it's brittle, that's the plate. Underneath that plate is the asthenosphere. It's still rock, yeah, it's still solid-ish somewhat, but it's hot enough to flow like glacier ice. You'd swear it's a solid, but over long enough of time, it creeps. And what the new model shows is that this layer isn't sitting still. It's flowing horizontally. It's sweeping east. So think of it how we could describe it as a weather, but made of rock, moving inches per year. They're calling it mantle wind. That's why it has that name. And what's driving it? We could say it's a ghost. It's a ghost. What do I mean with this? Millions of years ago, guys, you have to imagine it's like an old oceanic plate that was called the Farallon, slid underneath North America, and then it was sinking down. So that descent is still steering the mantle. So the volcano in Wyoming is basically being fed by the wake of a plate that stopped existing at the surface a very long time ago. That's why ghost. Now, the part that's actually clever, that flowing rock is hot, but it isn't liquid. That's the difference. That's the key difference. So how do you melt it? Well, you don't add heat. You take away the pressure. So I'm giving you now, let's call it the kitchen version, right? Let's take a sealed can of soda. It's warm, perfectly warm, no bubbles because the pressure is holding the gas dissolved in the liquid. Now crack the tap. You didn't heat it, you didn't shake it, you dropped the pressure and it foams instantly, right? Rock does the same. That's the interesting thing. So deep down, it is squeezed so hard that it stays solid, even at insane temperatures. So let it rise, even a little, and the squeeze comes off. And then it melts on the spot. So in geological terms, we call this decompression melting. Have you ever heard of this? Let me know in the comments. And it's the single most important sentence that I make in this whole video. Did you ever hear, has anybody ever explained this to you? Decompression melting. This is so important. So let's talk about the mantle wind for a second again. The mantle wind sweeps east. So it gets nudged upwards and it decompresses and it melts near the top of the asthenosphere. It's shallow, it's not deep. So the furnace was never a mile-wide chimney from one core. Forget about this. Forget about all these graphics that you still see floating around about Yellowstone. It's a sideways draft melting itself as it rises. So as it's rising, it's melting itself. So why is there no lava lake? Melting rock is only half of the story. So you still have to get it through the plate. And the plate is solid, right? It's cold and it's thick. So this is the second half of the finding. And it's the part that actually I keep thinking about the most. So that's why it's so important that I tell you this. So stay with me. The mantle wind, right, is pushing east. This mantle wind doesn't carry the heat. It shoves. And there are opposing forces pushing back from the west. So we have two forces, opposite directions, same slab of rock, and then the plate in between gets stretched. And again, I have to use this comparison. Pull like toughy pizza dough. It doesn't snap cleanly. It thins out in the middle, right? It gets weak, and it eventually opens up along a line. So that's what this new model says is happening to the lithosphere underneath Yellowstone. It's being pulled thin and it's being torn open, and that tear then becomes a channel, a pathway that lets melt migrate upwards far more easily than it ever could through an intact plate. And this is the explanation for that weird lopsided shape that they have discovered. It's not a dot because it was never ever a blowtorch like underneath Hawaii, for example. It's a seam. So that's why the heat leans southwest. That's the shape of the tear. And I have to tell you, this now kills basically the last little piece of this movie version that we often see. There is no gigantic underground lake of glowing magma under Yellowstone. There's just not. Everyone thinks, oh, there's this huge magma chamber underneath Yellowstone. It's not there, and it never was. Boof, guys. So what's down there is what geologists call a magma mush. So that's mostly solid crystals with liquid melt in the gasps between them. So it's not a swimming pool, it's a slushy, we can call it, like, or wet sand if the water were molten rock. And here it is. You can't drain a slushy. It doesn't slosh and it doesn't surge. And this is the good part. It does not erupt easily. So mush is stiff and it resists flowing. So if we have a truly liquid, ready to erupt magma body, magma reservoir, that only seems to form only briefly right before an eruption, and then it's gone. So I give you the scoreboard on the danger now. This is my honest opinion, and I'm not going to lie to you for like, oh my God, right? This finding does not mean that an eruption is coming. Researchers do not think we're due. This is good, right? So this mush is actually hard to erupt. So, but flip it over. If the eruptible magma only assembles shortly before the eruption, and that's the critical part, that's scary. Then the warning sign we've all been told to watch for, like the slow filling giant of a magma chamber over like centuries, may not be the warning sign at all, because this does not exist. Look at Iceland. They have the magma chamber underneath Svartsengi. They can measure it. It's gradually filling up to the point that it had before the last eruption. And then the next eruption comes, and then the next, and then it empties out, it fills again. So no. So how do we know if there's another eruption coming or not? This is now the problem. So nobody has ever watched a supervolcano do all that from the outside. So that's not, I'm not saying it's about to blow. That's something quieter and way more uncomfortable. We may have been watching the wrong thing. We may have been watching the wrong thing. So here, this is what you've been waiting for. Number 3, where is it going? Yellowstone is not where it started. Draw a line southwest from the park and you get to the Snake River Basin, right? If you look at the map, it's a long, flat, weirdly straight scar that is running across Idaho. So that plain is a trail of dead calderas. So basically we can say old Yellowstone. So the hotspot has been burning northeast across the continent for roughly 17 million years, and it has left one blown out crater after another behind it, and you can still see it. Wyoming right now, we could say this is its current address. This is where it's currently living. And this, the next point is interesting. That's what the researchers want us to know. For that entire journey, the system has been burning through crust that was relatively warm and relatively thin. So easy material, a soft target. And directly ahead of it, to the east, the crust changes. It gets colder, harder, and considerably thicker. So what does that mean? Nobody is saying that next week or like fairly soon something is going to happen, but it's generally an open question with basically with two possible answers, and they're not the same answer. So a thicker, colder lid could basically smother the whole thing. Heat spreads out, never concentrates, and the hot spot basically slowly loses. Yellowstone goes quiet permanently. Or a thicker, colder lid does what a lid does if we're thinking about a pressure cooker. The pressure that used to have an easy way out now doesn't. So we don't know which it is. We don't. That's the actual, and I have to say, unglamorous, slightly unnerving state of the science about Yellowstone. Because we can say the behavior of the next act depends on the source, and we just found out that we got the source wrong. So, as one of the authors are putting it, quote, "The plumbing is different than we thought, so every model of a future eruption has to be rebuilt to account for that." Take a step back and really actually look at what just happened here. Group of scientists ran the numbers on the most studied volcanic system on the planet. This is a place with more sensors, more seismometers, more papers written than on almost any other patch on Earth, right? And the headline picture, the one in every textbook, the one that you have drawn from memory, turned out to be wrong, not slightly wrong. Wrong direction. We had it going up. It's going sideways. And the one thing that is, for me, the most concerning thing, it's not that it's a story about a volcano and that is way more scarier than we thought. No, it's actually to discover how thin our confidence was to begin with. They kind of knew that something's off with their description. And we cannot look at the interior of our planet. Everything we know about this big machine that is right underneath us is basically echoes, math, and models. So which means still all of it is provisional. So in a few weeks ago when they found it, it was not that the ground underneath Yellowstone has changed, but the picture in our mind has definitely changed, guys. So if you like what you just heard, please subscribe. If you want to become a supporting channel member of this channel for behind the scene videos of my private life, click the join button. And if you want to fill me up with coffee to keep me going, link is in the description, buymeacoffee.com/silky. Thanks so much for everyone who's supporting this channel with your views, your comments, your likes, your supers. Thanks, guys, your coffees, and shout out to all my members. And check out this video because this will blow your mind. It's absolutely crazy what happened there, and this is something you should really be aware of. So see you in a second. Bye-bye.